Okay, we're back from the break. Actually, the break exercise is not much I can provide answers. We want to check the answers, so it's a matter to do it. So I'm not going to say anymore. Okay, I hope if you don't have finished, you can do it later. So for this half of the lecture number 5, we're going to talk about conservation laws in a field system, not just like a single particle momentum conservation, energy conservation, but for a field, for a system continuous medium. For example, you probably know the charge conservation in a field system is expressed as a continuity equation. Uh, for example, charge conservation is the rate of change uh, charge density is equal to plus the divergence of the current is equal to 0. Now, why is that a conservation statement? You can check by doing a volume integration of this equation. So I integrate both the first term to the volume, the second the volume. Okay. And for the first term, I can interchange differential times by to integration. So I integrate first, then so basically the first term tells the rate of change of charge in the volume V. Okay. The second term, I can use divergence theorem from this divergence of the volume integral divergence into a surface integral of a closed surface around the volume uh, by this J dot ds is element of the surface. Now remember, elements of the surface is always defined to be pointing outward from the volume. So therefore, this minus J is talking about the flow into the volume. So therefore, the rate of change or the rate of increase of charge is equal to the amount of charge that flow into the surface, into the volume. So that's a charge conservation. You cannot just get something for nothing. If you increase it, it must be something coming in. Now, this continuity equation can be written in terms of four currents in a very compact form. This simply the continuity equation written as the four divergence of the four current equals to 0. Divergence of the four current, because you can check that this del operator is ddt, and the 1 to 3 component is the del operator, and the current, full current, 0 component is charge, and the 1 to 3 component as the 3 current. So therefore, you multiply these together, you get this continuity equation. Now, again, to connect something remember Maxwell's he introduced a displacement current, which is the rate of change electric field, in order to have charge conservation. You know. So therefore, how does this come into our covariant expression of Maxwell's equation? Remember, put in the displacement current allows us to write the Maxwell's inhomogeneous equation as without the rate electric field term, you can't complete this thing. That's buried inside this. So therefore, the divergence of the F mu nu is equal to the full current J nu. Now, how does charge conservation? Well, because charge conservation is a full divergence. So I take the full divergence on both sides. See, I take d nu on both sides. So on the right hand side is d nu J. Now, how to show that's equal to 0, charge conservation? Because the left hand side, I have two terms of, I have one term, F mu nu, differentiate once with the nu and the differentiate second with nu. But the differentiation is commutative. It doesn't matter whether that difference is to dx nu or differentiate dx mu, the same. So therefore, in this part, the mu nu index should be symmetric, in which you interchange the two mu nu, it doesn't change. On the other hand, F mu nu, remember, which is anti-symmetric. So therefore, in this expression, I have a contracted two indices. One part is symmetric, other part is anti-symmetric. And we have shown in the exercise in the past, this has to be 0, because you can show something equal to minus itself. It has to be 0. So so therefore the charge conservation is automatically built into the Maxwell's equation. Now let's take a look at the full current again. So as what's the physical meaning of the elements of the full current, which is zero component, one, two, three component. The zero component is, remember we say is C times charge density. And so C charge density is the amount of charge in the volume dx1, dx2, dx3. Some amount of interval in the x direction and the y direction, z direction to make the volume. And the let's say the 1, 2, 3. Let's just talk the x component of the current, which is the flux density. So it's amount of C again. Uh, you know, amount of charge cross per unit time per unit cross section area. If the current flow in the x direction, the cross section area is dx2 at dx3. Then I multiply C on both sides. Okay. Now CDT is delta x naught, and this x2 x3. Okay. Now similarly, you can write the y component, z component. Now all this can be, these two expressions I can written more compactly as C times the amount of charge delta Q divided by for what I call del S mu. What del S mu is supposed to be a Minkowski three volume, okay? And that is, Minkowski four volume would be del X naught, X1, del X2, X3. That's four volume. But three volume means I'm saying that's just, we were talking about no interval in one direction. For example, uh, when del x mu means that the x is fixed, means this is absent from this. So for example, delta x naught is all term except there's fixed x naught, so there's no interval in the x naught. So then it was just the, the del x mu prime would be missing from the full volume. So that's becomes three volume, and same way delta x1 would be the delta x1 be missing. So you notice, so therefore for jx naught will be del cq with x naught missing. So therefore that's just this term here. For the j1 case, it will be this. It will be x1 will be missing. So it will be x naught x1. That's just this one. So this is just a more compact way of writing for all three components, four components, into to say the physical interpretation is the amount of things you want to relevant charge and divide by the three volume, okay, of Minkowski space-time. Now let's talk about energy momentum tensor or energy momentum stress tensor. Like conservation energy momentum field system can also express as a continuity equation. It's just something like like we did for charge. And here the square parenthesis nu is the full current density of the energy momentum of the field system. So first of all, this one is now must be at tensor rank 2 instead of like last time we talked for current, because while the electric charge is a scalar, then you divide by the free volume, you get a full vector. But that's for the charge case. But for the energy momentum current, it's the quantity itself is a vector, p mu, full vector. So therefore, when you talk about this amount of quantity per unit 3 volume, which is also have an index, so you had end of something with two indices. So that's be a rank 2 tensor, okay? Because the quantity you're talking about or consider being conserved itself is a vector, has one index, then the current itself is a 9, so you have two indices. That's two. So in other words, we're talking about the energy momentum conservation of a field system would be something like this. The full divergence of a rank 2 energy momentum tensor equals 0. So again, of course, you say, well, I don't know. What is the T mu anyway? So let's look at the physical meaning of the various elements of this rank 2 tensor, which can be written as a matrix. And each element supposed to have the interpretation of the amount, momentum, energy momentum for the mu index, and for the three volume has the nu index. So uh, let's say the T mu nu is a 4 by 4 matrix. I would like to know what are the elements, what the meaning of these elements. Let's look at the T00 first. Okay, T00 by definition is C delta P nu delta S naught. Remember, P naught is delta E over C, so C cancel, and delta S naught is just the full volume with the X naught fixing, which is missing. There would not be a delta X naught, so just delta X1. So that's just the volume. So therefore, the T00 term simply in term energy per unit volume, so it's energy density. So the T00 simply is the energy density. Okay. Now let's do 1, 2, 3 of the first row, okay, T01. Again, here is the 0 is giving the energy, and now the 1 means the S1 is just the delta X1 will be missing, just delta X0, X2, X3. Now, delta X0 is CT, so C times delta T. Delta X2, delta X3 is simply the perpendicular surface perpendicular to the X direction, one direction. So therefore, it's the transverse area. So therefore, it's energy per unit time per transverse area. So that's just flux. So that's just energy current density. Okay, it's a flux. For the 1, 2, 3 component of the first column is T10. It will be CTX1, for example. And then again, it would be what's missing because it would be 0, will be there's no delta X naught in the denominator. So that's equal to the momentum, in this case, X direction per unit volume. So this is simply the momentum density, momentum per unit area, per unit volume. Okay. Now let's look at the diagonal part of the 1, 2, 3, the 3 by 3 matrix part. Let's say look at T11. So we have P1 in the numerator and denominator. We should have a missing delta X1, and so delta X2, X3 is simply the transverse area, and now the del X, del P1, del X1 involves the rate of change of momentum in the X direction, but that's force. So that's force in the X direction. The C factor just cancels the X now. So force per unit area, perpendicular for per unit area, that's pressure. So this is pressure from force in the X direction, this pressure from force, perpendicular force in the Y direction, this pressure from force in the Z direction. Okay, so the diagonal element, the 3 by 3 part, is simply pressure. It involves perpendicular transverse force. Now you can work out for the off diagonal part, the same thing, except now it involves the paraforce. So it's shear, it's a shear force. Okay. So let's again. So the T00 energy density, and the first row is the energy flux, and the first column is the momentum density. The diagonal element of the 3 by 3 is pressure, and off diagonals are the shear forces. And in fact, one of the key property we're going to use is energy momentum tensor is symmetric, in which I interchange row or column, I get back itself. Okay, there's no minus sign. What I will do is going to show the energy flux equal to momentum density. For this 3 by 3 here is a little more complicated, and I'm not. In fact, we're not interested in shear force part at all. So let's just look at the fact that the energy flux equal to momentum density. So here's the energy flux, here's the momentum density. Okay, so instead of writing all the momentum, I choose to write momentum as the longitudinal displacement and the transverse cross-section area. So that's the same thing as the Now, the question is whether these two quantities are equal. Well, I claim it is because, well, first I cross out the transverse area, so what's left is just delta C prime over uh, C prime over du over d equal to, claim if this is true, is delta xi over ct. But there xi over delta t, that's velocity in the ith direction. Okay, so so the pressure, so the momentum, not this is not pressure. So the momentum over the area, over the energy, is velocity over c. But that's exactly the relation we had before. The momentum c over energy is v over c. We had used it before. So therefore, this is true, and the energy flux equal to momentum density. And in general, we can show that's uh, T mu nu equal to T nu u. So it's a symmetric tensor. Now, all these things you say, well, I'm haven't worked with energy momentum tensor before, so but I want to connect to something you already know. You probably should know. If you work out the energy momentum tensor of the electromagnetic field, I'm not going to work out here. What you'll find the T00 term simply is, or I'll say work out, meaning you're finding expression of the T mu nu in terms of the electric field and magnetic field. You'll find T00 simply E squared plus B squared. But that's just the energy density we know from electromagnetic courses. So, and then check what we said, T0 should be energy density. And for the momentum density, or for the flux, you can work out some E cross B. That's just the uh, Poynting vector, which we know has the interpretation of the momentum density. So all these things check with something you already know. So don't give the T mu so totally foreign to you. Okay. Now, to us, it's very important to know the energy momentum tensor for the ideal fluid. Ideal fluid means it has no shear force, no viscosity. It's only perpendicular force. So, in particular, we can work out the case for the T mu nu in the ideal fluid for the so-called the co-moving frame reference, in which each fluid element carries its own position labels. So therefore, of course, if you carry your own labels, however you move, you stay at the same label. So it's effective. It's the rest frame of the fluid. Okay. In that case, the energy density simply is the rest mass density times c squared. So therefore, you expect it to be rho c squared for the T00 part. And for the 1 part, 2 part, 3 part, remember that's the pressure in the three directions. And for an ideal fluid, there's no preferred direction, so therefore should be the pressure, same value for the 1, 1, 2, 2, 3. Now here is the P stand for pressure, not for momentum. Up to this point, we often use P as momentum. Here we're talking about pressure. Okay. And then there's no shear force, no viscosity, so all these terms here will be zero. Because and zero for the first column, first row, that's because we are affecting the rest frame. There's no flux, no. Now, this is an expression of the idea fluid energy momentum tensor in the one frame reference. What we're interested in the expression that value for all frame reference. Okay, so we claim we want to write the T mu nu in some tensor expression in terms for velocity, which is tensor, and the metric, which is a proper tensor. Can be worked out. That's the energy momentum tensor for rest frame is the proper density, or the rest frame density, plus the pressure over c squared times the full velocity with index mu, full velocity index nu, plus pressure times the metric eta mu nu. Okay, so this is scalar. This is tensor rank 2 because each are proper tensor 1 together is rank 2, and eta mu nu, of course, is a tensor of rank 2. Now, claiming that this is the covariant expression for the ideal fluid T mu nu. What I'm going to do to check that in the co-moving frame, in the effective rest frame, this is just what we set out to find. Now, in the co-moving frame, the particle at rest, so therefore the full velocity reduced to just because v equals 0, gamma equal to 1, so it's just just have zero component c. That's it. There's no other component. Okay. So if this equal to uh, just only zero component to equal to c, and the c, so that I have rho plus v squared and c squared in the one and 0 everywhere else from the first term. For the second term is p times the inverse metric, which is minus 1, 1, 1, 1. So you know that you put these together, and I have rho c squared uh, plus p, and I have, from here I have minus p. The pressure just cancel, so I left to rho c squared. And for the 1, 1, 2, 2, 3, 3 component, I only have, because there's all 0 here, so I can reproduce this. Okay, so therefore, this expression indeed reduced to the expression, this one, for the co-moving frame, for the rest frame. But this is a tensor expression. If it's true one frame, it's true all frames. So therefore, this expression for energy momentum tensor valid for all frames because that is a tensor expression. Okay, all these sounded pretty complicated to you. You ask, how much do I need to know? Well, all you need to know for energy potential are the following aspects. You need to know that tensor energy potential appears in Einstein field equations. So when we talk about Einstein theory for general relativity and cosmology, we need to at least know. You may not work with it, at least know this. You have energy momentum tensor. So all we need to know about energy momentum tensor is the tensor is basically the four current of the four momentum vectors. Okay, and it's symmetric. And T00 component is energy density. Okay, and energy momentum conservation can be written as the four divergence of this. And for the ideal fluid in the co-moving frame, it's energy mass density times c squared and pressure on the 1, 1, 2, 2, 3. That's all you need to know for the rest of this course about energy momentum tensor. Now, this end of lecture 5, remind you we talked about two tensor rank 2, the electromagnetic field tensor F mu nu, energy momentum stretch tensor T mu nu, and also to know that the conservation law can be expressed as the four divergence-free conditions. For example, if the simple current is four divergence of current equals 0, for the energy momentum conservation, simply the T mu nu have no divergences. Next lecture, we're going to talk about space-time diagram, which turns to be particularly helpful to understand the causal structure, cause-effect structure of the space and time. And also, we're going to we talked about Einstein's original formulation, special relativity, kinematics, and we're talking about Minkowski's geometric formulation. So I want you to have a simple place to see what's all the advantage of the geometric formulation. So we're going to have a summary of the advantage of geometric formulation. Then we are ready to start the GR study. Before we start GR, we're going to review the Newtonian theory of gravity when it's written in terms of gravitational potential, and then we're going to talk about Einstein's motivation to go from special relativity to general relativity. Okay.